will be given by Ritabrata Bhattacharyya from Math first year. He is broadly interested in representation theory, certain aspects of algebra, and aspects of analysis. So he'll be giving a talk on compact groups and the Peter Weyl theorem. So over to you, Ritabrata.
So in this talk, we will mostly talk about representation of compact groups. So before that, I'd like to give a quick overview of representation of finite groups. This will help you to understand, this is necessary to understand representation of compact groups. So we'll start with it. Wait, what? Wait. So the general aspect, the motivation of representation theory is to study several objects by studying how they act on different objects. For example, by representation of a group, we mean a vector space together with the action of the group on it. So we'll study the group by seeing how the group acts on different vector spaces. This helps basically representing each group element by a matrix. So the advantage is we can convert group theoretical problems into linear algebra problems, and linear algebra is much easier to study than group theory. So this helps us to reduce a lot of difficult situations to some easier situations. So again, a representation of a group is a vector space equipped with the action of the group on that space. In fact, even if a group is acting on any set, we can make a representation out of it. If G acts on a set S, we can construct a vector space with basis S by taking formal linear combinations, and this will extend to action of the group on a vector space. So it's convenient to study vector spaces because they have more structure. So here are some examples of representation of finite groups. So our symmetric group Sn acts on C power n by setting sigma dot z1 dot dot zn equal to z sigma inverse 1 dot 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 z sigma inverse 1. Basically, it acts by permuting the coordinates according to the permutation. This is called the permutation representation, and this plays a pretty important role in representation of symmetric groups. We'll not talk about it here. So let's move to the second example. So our cyclic group Z mod n Z acts on C2 by, so it's a cyclic group is generated by a single element. So basically, however the element the generator acts, it will just give us how every element acts. So the first element, generator 1, it acts by rotation by 2 pi by n. Similarly, element 2 will act by rotation by 2 into 2 pi by n, and in so on. Like the element n will act by rotation by 2 pi n by n. Similarly, one more obvious example is for any vector space V, the general linear group, that is group of all invertible linear transformations on V, that acts on V in the obvious way by setting like the maps act on the vector in the usual way, T dot V equal to T of V. This is called, here is another important example, it's called the regular representation of G. In the previous example, see, the groups we had were very particular, symmetric group, cyclic group, but we cannot develop a general theory based on these examples. This is why the next example becomes very important, because it's an example of a very arbitrary group. So basically, if you're given any group, any arbitrary group, you can get a God-given representation of that group. This is called the regular representation, and we'll see it helps us to classify all different types of representations of that group. So this is very important. So KG stands, we call the KG to be the group algebra of G over K. It is all functions from G to K that is non-zero at only finitely many points, or functions with finite support, whatever you may call it. We can represent each such element by a formal linear combination of field elements and the group elements. These are formal symbols where the element kg represents at the value of the function at G. And this is a finite sum because like all other kgs will be 0 because the function is non-zero at only finitely many points. And given any arbitrary such element summation kh dot h, we can let the group act on it by just left multiplication. keep the scalar as it is, act on each slot by left multiplication. This is called a left regular representation of G. Similarly, we can define the right regular representation of G by setting G dot kh dot h summation kh dot h equal to summation kh dot hg instead of gh. Just interchanging h and g. So after some examples, we'd like to develop some language of representation theory. So this is common in most parts of algebra. You define an object, you need to define sub-objects, maps between objects, and so on. So representation of a group is basically a vector space together with an action of the group. So by a G invariant subspace or a sub-representation, we mean that a subspace of that vector space on which G acts, which is stable under the action of the group. That is, if we restrict action of each G on the subspace, it becomes an operator on that subspace, invertible operator. We call such things as sub-representations, G invariant subspaces that are stable under the action of the group. Similarly, you can define simple objects, like we call a representation to be irreducible or simple if it has no proper non-trivial sub-representations. For two representations V and W, like two different actions, the first action is given by phi and the second action is given by rho, we can define a morphism or a G linear map between V and W to be a linear map that respects the actions of the group on both domain and codomain. That is, T of G dot V equal to G dot TB for every group element and for every vector. That is, you can think that the group element is acting like a scalar or something. You can think that it's not the case, but yeah. Similarly, two representations, we call them isomorphic or equivalent if they are same as representation. That is, see, representations have two data, a vector space and an action. So their isomorphic means the underlying two structures has to be same. So the vector space structure has to be same means there should be an isomorphism from V to W, and as representations they has to be same implies the isomorphism of vector spaces has also be isomorph as a G linear map, like isomorphism as a G linear map. Similarly, for each morphism, image, kernel, they are all sub-representations for respect of domain and codomain respectively. In fact, if we have like all G linear maps from V to W for two representations, that also forms a sub-representation of our home VW, like all sub-representation of home VW. So with these definitions, we try to, let's see what more we can do with this. So given some representations, we want to make more representations also out of it. So we have vector spaces as representation. So what can we do with vector spaces? We can take direct sum, tensor product, or symmetric power, exterior power, these things. Like all multilinear gadgets, we can try to turn them into representations. We'll not talk about symmetric or exterior power here, but we'll try to see one or two small examples. That is, if we have two representations, we can make the direct sum also representation, like the direct sum of vector spaces and tensor product, in the obvious way by letting the group act on each slot. So G dot V comma W is G dot V comma G dot W. It defines a representation structure on the direct sum V direct sum W. In the first slot, G dot V is the action of G on V. In the second slot, G dot W is the action of G on W. But these two dots are not same dots. It's just a notational convenience. The first G dot V is basically phi of G times V. Second G dot W is rho of G times W. In most of the scenarios, we'll omit the notations phi and rho as long as the meaning is well understood. And we can see that for any group element, the matrix of, if we have a representation of G on V and W, so basically representing each group element as matrices on V and matrices on W, then if we represent that group element as a matrix on V direct sum W by this way, it becomes just the block direct sum. And similarly, for the tensor product, it becomes the canonical product of matrices. These things are easy to check by hand. Now, similarly, in algebra, semi-simplicity is a very important concept. In general, we have defined what we call a simple representation. or in the language of representation theory, a simple object. In algebra, like given simple objects, one most natural thing to do is to try to define semi-simple objects that are basically direct sum of simple objects. Many nice things holds about them. So in our context, we call a representation to be semi-simple if it is direct sum of simple representations. And this part is common. Like if an object is direct sum of simple objects, is same as saying every sub-object have a complementary sub-object. This is more like common in module theoretic perspective. I will not talk about that, but let's assume this for a moment. That is, V is a direct sum of simple representations is same as saying for each sub-representation W of V, there is another sub-representation U of V, so that V decomposes as W direct sum U as representations. So one thing is to notice that given any subspace W and V, we can always write V equal to W direct sum U for some U by completing the basis. But the problem is that W is a sub-representation, but U might not be a sub-representation. So we cannot do this always. I mean, in otherwise, any representation will be semi-simple. Here is an example for which it does not hold. So in this case, our group will be the additive group of integers Z. And we'll try to represent each integer by a matrix. We'll try to let Z act on R2 or equivalently C2 in the following way. Each integer A acts as the matrix 1A 0A as given here. And you can see that it leaves x-axis fields. Like if you just take any x comma 0, it maps x comma 0 to x comma 0. So it has an invariant subspace, so it is not simple. But we cannot write it as direct sum of two simple representations. Why? See, Z acts on R2, so it is acting on a two-dimensional space. So if we already have a one-dimensional invariant subspace, which is x-axis. So if it decomposes as direct sum of two representations, then it will basically be direct sum of two one-dimensional representations. Now, one-dimensional representations are given by like 1x1 matrices or just single numbers. And since the action of a direct sum is basically slot-wise action and the matrix also becomes log direct sum, in that case, our phi a should be equal to some rho 1a and rho 2n. Rho 1, rho 2 basically are the one-dimensional representations which we are trying to find. But this will immediately imply that phi a has to be diagonalizable, because there are 1x1 matrices. But this is false because this matrix 1A 0 is not diagonalizable. It is a very well-known fact that a matrix is diagonalizable if and only if its minimal polynomial has no repeated roots. So its eigenvalues are 1, 1. So its minimal polynomial is either x minus 1 or x minus 1 whole square. It cannot be x minus 1 because this matrix is not identity matrix, and in the other case it will have repeated roots. So in this case we see that we have an representation. It has an invariant subspace, but we cannot write it as direct sum of invariant subspace because the complement might not be invariant. We will see that for finite groups this scenario happens very rarely, which will be our next thing to talk. Before that, we need some machinery, some gadgets to develop. So again, we want to, like, given some representation, we want to develop a theory. Like where we have some representation, we want to build more representations out of it. So if we have a representation of V of G, that is if G acts on V, we can make the dual space of V star also representation of G. That is if G acts on V, then G acts on V star also in a natural way. Basically what we need to do, given a linear functional f, we need to define another linear functional G dot f. We define it in the following way, that is G dot f, it operates on V as f of G inverse dot V. This is one of the natural things to do because we need to apply G dot f on V. It should be related to f and G both. So what the most obvious things that you can do is either do it f of G dot V or f of G inverse dot V, but one may ask why are not doing f of G dot V? That seems more natural than G inverse. So the thing is, by action we mean usually a left action of the group. We can check that if we define G dot f of V to be f of G dot V instead of f of G inverse dot V, then this action will give a right action on V dual. This is a common thing, that is if we apply the group element inside a function, then the left action converts to a right action, and if it was a right action, it converts to left action, and vice versa. I mean, it's evident. Like suppose you are given a graph. If we graph of a function f of x, if we try to do f of x plus 2, then the graph shifts 2 units downwards, not upwards. Like it goes in the reverse direction. It holds like in a similar way here. If you apply left action inside the function's argument, the resultant thing becomes the right action. So to reverse that change of order, we multiply it by an inversion, because inversion is also order reversing. GH inverse is H inverse G inverse. Like we do two types of order swaps in a row, so to cancel the order swap. So this is our definition of how the G will act on the dual space of V. Similarly, if V and W are representations of G, then the homomorphism from V to W, it is also a representation of G in a natural way. We have to do again one thing, that is, for a given linear map T from V to W, we need to define a linear map G dot T from V to W. So this is our definition, that G dot T of V should be G dot T of G inverse dot V. So one may ask, how can we guess this definition? So one thing we can do is, I'll not do it here, we can check. So home VW, it is naturally isomorphic to V star tensor W. This is a very well-known isomorphism. We have already defined an action of G on V star naturally in the above line. We also have an action of G on W. So in the previous slot, we have already defined if G acts on two vector spaces, it also acts on its tensor product in a natural way. So from G acts on VW, it will mean that G will act on also V star and W in a natural way. So by the previous slide, it will also act on V star tensor W in a natural way. We'll find that action, and by the isomorphism, we'll take the action on home VW. We'll say that the action is exactly same as this. We need to do some work, but at the end, we will find this definition. For a representation V of G, we define a fixed subspace of the representation. That is, on the subspace of V on which the G acts trivially. That is, every group element acts as the identity operator on it. It is easy to check that Vg is a subrepresentation of V. In particular, if G is finite, then we have a very useful thing. We have a linear map A from V to Vg, given by A of V to be the average of all group elements acting on V. Like we let all group elements act on V, G dot V, we take their average, and we take their average. This is called the averaging map. We can see that this is a projection onto Vg. That is, for any vector V in V, A of V, this average lies in the fixed subspace Vg, and it is the identity map on Vg. These are easy to check because if we left multiply, then if G varies over G, G of G times H will also vary over G. This is easy to check. You can check by hand. This map is very important, which we'll use in the next proof. So this theorem is called Maschke's theorem. It says that G for any finite group G and the field K, so that characteristic of K is either 0 or it doesn't divide the it's not P. It should be size of the group G. It's a typo. So let G be any finite group and K be a field such that either characteristic of the field is 0 or the characteristic doesn't divide the size of the group. I'll share the slides and fix this typo. Then it will say that any finite dimensional representation of G is semi-simple. In the previous slide, we have seen that if we take our group to Babylon group Z, then this is not the case. They are non-semi-simple representation. In fact, there are many of them. But we'll see that this theorem says that if you have a finite group and it acts on a vector space over a field whose characteristic doesn't divide size of the group, then any representation will be semi-simple. That is, you can write it as direct sum of simple representations always. The case when characteristic divides the size of the group is very difficult. Like we'll see. Like mostly what we'll do is representation of characteristic 0, mainly over the complex number C. But in characteristic P, things become like unexpectedly very difficult. We need a lot of machinery to develop. We need many facts from algebraic number theory also. We'll not talk about that here, but it's a fact. So again, what we need to do to show that it is semi-simple, given any sub-representation, we need to find a complement which is also a sub-representation. That is, G acts on V, a finite group is G is acting on V. If V is itself simple, then it is already semi-simple because it is direct sum of with itself, like it's nothing to do. So assume there is a proper non-trivial sub-representation W. We need to find a sub-representation U so that V equal to W direct sum U holds. In the usual vector space scenario, this U always exists, but in our scenario, this U might not be semi-simple. This U might not be invariant under the group action. We'll see that if the group is finite and characteristic doesn't divide size of G, we can always find such U. So we note that we have always our usual projection map pi from V to V onto W. That is, you can write V equal to V directs W directs something, and with that, like take the W component on it and project onto W, the usual projection. And for projection maps T, we can always write V as direct sum of kernel and image. This is standard linear algebra fact. In which case our image of pi is W. So we can write as V as kernel pi direct sum W. Now W is a sub-representation, that is according to our assumption. Now the thing is, the kernel pi, this might not be a sub-representation. It might not be invariant under the action of the group. We have seen that a kernel and image can be sub-representations, but the sufficient condition is that our map should be also morphism, that is the G linear map. But this projection map might not be G linear. This kernel might not be invariant under the group action. So what we'll do, we'll try to find another projection which will serve as pi, but it will be a G invariant projection. That is, we want to find another projection onto W which is invariant the action of the group. And if we can do that, we're already done. Because we can always write, in that case, we'll be able to write as V equal to kernel of pi tilde direct sum W. But in this case, pi tilde will be a morphism of representations, that is a G linear map. So in that case, kernel of pi tilde, that will also be a sub-representation, right? And we'll be done in that case. So here is what we need to do. Given pi in home VW, which is a projection, we want to modify pi to pi tilde in such a way so that pi tilde still remains a projection onto W, and it is in home G VW, that is a G linear homomorphism from V to W. This is our target. In the previous slide, we defined the averaging map. We'll use this map to get this. So note that this home G VW, this was a sub-representation of, this was a subspace of home VW, but we haven't made home VW a representation in a canonical way. So home VW becomes a representation of G in the following, that we already defined before. So according to our previous slides, given any representation of V, we can define as fixed subspace. So since V and W are representations of G, home VW is also a representation of G in this following way: G dot T of V equal to G of T of G inverse dot V. So we can also talk about its fixed subspace of this representation, of the home representation. We can easily check that by this action, the fixed subspace of home VW is same as all G linear maps from V to W. This is straightforward to check by hand. And now basically we can, in the averaging map definition, we can replace V with home VW. So the point is that even any map, like any linear map from V to W, we can take the image of it under the averaging map, and the resulting map will be a G linear map from V to W. This is what we do. From V, we can have a map from V to VG. Instead of V, we are taking home VW. That will give a map from home VW to home G VW. That is, given any linear map, we can take its image and its image under the averaging map, and this image will be a G linear map from V to W, which we can think as we are averaging a map to make it a G linear map. So A of pi will be 1 by summation G, 1 by size of the group, and summation G dot pi. But this dot is the action of G on home VW, because the averaging map is from home VW to its fixed subspace. Now how does G act on pi? According to the previous definition, G dot pi of V should be G dot pi of G inverse dot V. This is our definition. So we can define pi tilde to be A of pi, that is our map becomes V goes to 1 by size of G dot pi of V. Basically A of pi is this map, and G dot pi of V is G dot pi of G inverse dot according to the previous definition on how G acts on home. So basically you have averaged the map pi over the group to make it into a G linear map. We can check by hand that pi tilde still becomes identity map on W, and it's a projection onto W. And in this case we are done. We have found our pi tilde so that it is a projection onto W and it's also G linear. So we can write V as W direct sum kernel of pi tilde. Since pi tilde is G linear, kernel of pi tilde will be a sub-representation. So we can write V as direct sum of two sub-representations. And we are done in this case. So one might ask, why did you use that characteristic is 0 or it doesn't divide the size of the group? The thing is, the map averaging, we have defined 1 by size of G. That means the size of group has to be invertible, has to be an invertible element in the field. This is why because of zero division of issues, we take characteristic to be either 0 or at least it should not divide the size of the group, so that 1 by G is well defined. That's it. So the upshot is that using an averaging thing, we have obtained such an important result. So here is our upshot. In general, semi-simplicity is a very nice condition because we can break semi-simple objects into simple sub-objects. And we can count multiplicities of simple parts. That is, we can count how many times a particular simple part appears. It's like prime like we can write any integer as product of prime powers. Here prime numbers are simple objects and the powers are basically the multiplicities. Vector spaces, we can also do the same. Given a finite dimensional vector space, we can write it as direct sum of subspaces, and we can count how many times copies are there. For vector spaces, this is very simple. Anyways, but semi-simple objects are nice in this way because we can do a lot of things with multiplicities and many nice things holds. But this nice thing doesn't hold for representations of infinite groups in general, because the concept of averaging may not make sense in general. But here is one nice thing which we want to develop in this talk is that if our group is a topological group which is locally compact, I'll define what is a topological group in the next slide. Then we can do a similar thing. We can define a measure on the group which will allow us to integrate over the group. We'll integrate functions defined on the group, and we can do the same averaging process with sum replaced by integration by thinking integration as a continuous sum heuristically. Basically, the averaging process 1 by size of the group summation over G over G. This integration over G will serve the analogous purpose for the sum. Basically, we'll replace sum with integral and many analogous things which we'll see now. So till now, do you have any questions?
So this measure that we'll end up getting in the integral, we'll also need that to be G invariant, right? In the analogous way. Somehow.
Yes.
Okay.
I'll not talk about the construction of the measure because I want to mostly talk about examples or general theory, and the construction of the measure is not very important because if I give you a randomly chosen topological group, you cannot try to construct a measure from the proof, right? The proof is very abstract. You cannot construct things from there. The proof is interesting, but it will not serve any purpose for this talk. So I'm omitting it. I'll just state the properties of the measure. We call this a Haar measure. And in particular, all finite groups are compact in obvious way. And in this, basically in the finite case, the measure just becomes the counting measure. And this average becomes the integral. So here is the definition of a topological group. This in a general philosophy is that if we define two structures on a set simultaneously, we would also want those two structures to respect each other. Like if we have two structures that don't talk to each other, are very independent of each other, is same as studying two different structures separately. We cannot link them at all, and that will not be helpful to us. So if we have like two structures, like I have a group structure together with a topological structure or together with some measure, anything, we'd like them to structure each we'd like them to respect each other's structure. In a similar way, like we define the linear, like the morphism between representations, we like the linear map to be also invariant under the action of the group. Otherwise, we cannot link them together. Like how will a linear map help us understanding the action of the group? In a similar way, so a topological group is a group which is also a topological space, but the topology structure and the group structure, they need to respect each other, which you can do in the following way by making all left multiplication and inversions continuous maps with respect to the given topology. Okay, but yeah, this thing is important. Basically, for any fixed G, the map H goes to GH is continuous. It's not same as saying that from the map from the product group to G is continuous. This is a stronger condition. So we impose this condition. G comma H goes to GH, the multiplication map is continuous, and the inversion map G goes to G inverse is also continuous with respect to our given topology. Whatever topology we are enrolled with the group. So a topological space is called locally compact if for each point there is a neighborhood whose closure is compact. Basically, it means that the small parts of the topological space looks like small parts of a compact space. These are very common examples of locally compact groups. The additive groups Rn and Cn, in particular R and C. Or any finite group with discrete topology. They are all topological groups. The unit circle S1 is a topological group. In fact, the GLN are GLNC orthogonal and unitary groups, like group of orthogonal matrices and unitary matrices. They are also locally compact topological groups. Their groups and their topological spaces, they're pretty easy to see. Why they're locally compact? Because open subspace of Euclidean spaces. GLN or GLNC are open subspace of some Euclidean space, and Euclidean spaces are locally compact, and open subsets of locally compact spaces are also locally compact. So here is our theorem about the measure. It's called Haar measure, and this is Haar's theorem. So we take G to be any sigma compact, locally compact hausdorff topological group. So there are two terms, sigma compact and locally compact. Sigma compact means it's countable, the spaces is a countable union of compact sets. And locally compact means that we defined in the last slide. That is, each point has a neighborhood whose closure is compact. So this hausdorff condition can be relaxed sometimes, but we'll try to make it hausdorff for our convenience, because we'll try to use a lot of theorems from topology that might not work if our group is not hausdorff. But after proving this for hausdorff, we can reduce to non-hausdorff in many ways. I'll not talk about that here. In our talk, we'll assume most of the topological groups to be hausdorff. So the theorem says that up to multiplication by a scalar, there is a unique Borel measure. That is, Borel measure means a measure that is assigned on a measure space generated by open sets and closed sets. Like Borel measure, you can think it as generated by like this. Here are measurable sets are basically countable union intersection complements this of open and closed sets, like that. Up to multiplication by a scalar, there is a unique Borel measure that satisfies, which is finite on every compact set. We can approximate any set from above by open sets and from below by compact sets. That is, for any Borel measurable set E, mu of E is infimum of all mu of open sets U that contain C. Basically, you can approximate from above by open sets, and similarly, you can approximate from below by compact sets. And this is most important, is that it is left invariant. This is C. We are defining a measure on a group. So again, we need some compatibility with the group operation and the measure. This is left invariant. That is, it is basically if we take a G dot E, that is translate of E under the action of group, then their measures are same. Basically, the measure is invariant under left multiplication. One nice example will be R plus. We have the standard Lebesgue measure on R plus, which is our length. or basically how we define Lebesgue measure, it is translation invariant, because in that case our additive group and G dot E will be like basically X dot E will be X plus E because we have additive group, and measure is clearly translation invariant for real numbers in the Lebesgue measure. This is one particular example. The thing is, you can, on any locally compact group, we have such a measure, which is left invariant. Similarly, we can construct a right invariant measure on G, on the locally compact group G or sigma compact, whatever hypothesis we had, by setting mu tilde of E dot G to be mu tilde of E to be mu of E inverse. E inverse means E is a G where space is a group, so inverse makes sense. E inverse means we take each element of E and take their inverses, which is our E inverse. We define mu tilde of E to be mu of E inverse. Inversion is order reversing. So basically, the left invariance under the inversion will translate into right invariance. But however, we need to be careful. We are not saying that every left invariant Haar measure is automatically right invariant. That is, we are defining another right invariance measure mu tilde from mu, but this mu tilde and mu, they may not be equivalent measures. They might be entirely different. But in fact, for some locally compact groups, we can formally prove that we cannot construct a Haar measure which is both left and right invariant. But we'll shortly prove that if we have instead of locally compact, we have some stronger condition, that is, if our group is itself compact, we can always find a Haar measure which is both left and right invariant. We'll prove this now. We need some machinery for this, which we'll define now. So before this, we'll just recall one thing, that whatever measure we defined on our locally compact group, it was up to multiplication by a scalar. That is, if we have any two Haar measures on a particular locally compact group, any two left invariant Haar measures, then they will differ by just a scalar. We'll use this fact to construct a function. Basically, fix any group element G. Then we have the following function, mu G of E is to be mu of E dot G. We can see that this gives another left invariant Haar measure. Why it is left invariant? Because we are multiplying G from the right, and basically we'll do mu of H of E, and H doesn't affect from the right, so it will be still left invariant. So from each group element G, we can construct another left invariant Haar measure on G. Since left invariant Haar measure is unique up to scaling from the previous theorem, we can say that there is a constant such that this new measure mu G is a scalar multiple of our original measure mu. Now this constant is clearly dependent on G because the new constructed measure was dependent on our group element. For each group element, we are constructing a new measure. So the constant will also depend on the group element. We call this scalar to be delta of G. This function from G to R positive, R non-negative, that is G is going to delta of G. We call this the modular character of the group. In fact, in the representation of locally compact groups, we'll see that this function is very important. Well, for compact groups, we'll see that this function is a trivial function, but for locally compact groups, it might not be trivial. And how this function becomes of great importance. So we can see that if our modular character is trivial, that is, if delta of G is 1, then it will clearly mean that mu is also right invariant, because it will directly mean that mu of E dot G equal to mu of E. So we need to show that every we can always find is not true in the glue text. It will mean that for a compact group, all left invariant Haar measures are also right invariant, which we'll prove now. You can see that since we defined mu G of E to be mu of E dot G, and this is same as delta G times mu of E, it is enough to show that for compact groups, this modular function is trivial. It will automatically mean that any left invariant Haar measure is also right invariant, which we'll prove now. In group theory, characters means homomorphism from the group to some multiplicative group of some field. So we call it modular character means this is also a homomorphism, which we'll prove right now. Till now this measure and what we're going to prove now, the target. Is it clear? Okay, so I'm moving. So first we'll show that delta is a continuous group homomorphism from G to R cross. We need the continuity because otherwise, like given any group homomorphism from G to K R plus, they may not be trivial. We need the continuity. Otherwise, we have G to be compact. If it's not continuous, we cannot use our compactness. This is important. So by definition, we have delta of G to be mu of Eg by mu of E for any measurable E with positive measure. To show that delta G is always positive, it is always non-negative is trivial, but to show that it is never zero, we need to find a measurable E so that mu of E and mu of Eg, none of them are zero. According to our construction, we note that this Haar measure is positive on every compact set. We'll use this. So it is enough to find E so that mu of Eg is greater than 0 and mu of E is also greater than 0. We can pick just E to be Kg where K is any compact set. Then basically mu of E is clearly greater than 0 because see, multiplication by G is a homeomorphism. So K is compact means Kg is also compact. Translate of basically its image of K under the homeomorphism G. I mean, we don't need homeomorphism, it's just continuous is enough. So Kg is compact and mu of Kg is greater than 0. We can just pick delta of G to be mu of Kg by mu of K. And both are non-zero, so mu of G is non-zero for every G. I mean, we can also prove it alternatively, which is not necessary, but it just proves a nice fact about Haar measure in a short way. That is, it is also, our Haar measure is also positive on any open set, which we can do in the following way. Pick any compact subset, and basically we want to show that mu of E is greater than 0 for a fixed open set U. Given any compact subset, we can cover the compact subset by all translates of that open set. Basically all AU where A varies over G. Then by compactness, we can clearly find like enclose it inside a finite union of these open sets, like union of AIU for some finite number of AIs. We can use basically our basic properties of measure, that is its subadditive and so on. Basically mu of K is positive, it is less than equal to summation mu of AI of U, and by left invariance of the Haar measure, it is same as mu of U. Clearly it will mean that some positive integer times mu of U is positive, so mu of U is positive. And in particular, we can take delta G to be mu of UG by mu of U. That will also work. The homomorphism property directly follows because delta of GH is mu of EGH by mu E. We can just do a cross multiplication and you can write it in the following way. It directly tells that it's a homomorphism. So the only thing that we need to prove is that delta is a continuous homomorphism. Again, since G is a topological group, to show that a map is continuous, it's enough to show that it is continuous at 1, at the identity element. So we fix any compact set and any epsilon positive. We need to show that if our group is very close to 1, then the delta of G is also very close. Close to 1. These two ones are different. One is the identity in group element G, and one is one in of real numbers. Whatever, it's a notational thing. So by our outer regularity, that is, we can approximate the compact set above from open sets. For any epsilon, we can find an open set U so that mu of U difference K less than epsilon, or equivalently mu of U less than equal to mu of K plus epsilon. Since mu of K is positive, we can replace epsilon with epsilon UK to get that mu of U is less than equal to 1 plus epsilon times mu of K. Since K is compact, we can find a neighborhood V of 1 so that K times V is also inside U. We can do this basically because the multiplication is continuous. These type of arguments are pretty common by taking unions and intersections, but I am still writing this argument. With the continuity of the multiplication map for each A in K, A equal to A times 1 is in U, so we can find neighborhoods V of A and W of 1 so that VA times W is inside U. And this VA covers K, we can extract a finite subcover. We can take V to be our intersection of all these corresponding WAIs. and this will directly imply that k times of V is inside U. Basically, it means that if a compact set is inside some open set, then an open translation of that compact set is also inside that compact set, inside that open set, whatever. So for G in V and Kg subset of U, we can write delta of G equal to mu of Kg by mu of K, and mu of Kj is subset of U. So mu of Kj is subset less than equal to mu of U. And mu of U by mu of K is less than equal to 1 plus epsilon by our construction. It means that if G is in, basically, I have found a neighborhood around 1. This V is a neighborhood of 1, so that if G is in that neighborhood, delta of G is less than equal to 1 plus epsilon. This proves like continuity from above, like continuity from right. Now we need continuity from below. We can prove this because of the group structure. We can actually mimic the same thing, but we don't need to do that. We'll try to use some clever arguments from group theory. Basically, for any G in V, K is subset of mu G inverse. So for any H in V inverse, K is subset of UH. So we can write in delta of H to be mu of UH by mu, and basically mu H contains K, so mu of mu H is at least mu of K, and mu of K by mu of U is at least 1 by 1 plus epsilon, which is greater than or equal to 1 minus epsilon for epsilon to be sufficiently small. And we can basically take, in this case, we took our V inverse to be our neighborhood, and in the previous case, for continuity from above, we took V to be our neighborhood. Now we can just, for the total argument, we can take to be intersection of the neighborhoods. So we have found a neighborhood which is V intersection V inverse around identity elements, so that if G is in that neighborhood of the identity element, mod of del G minus 1, it is less than epsilon. And this clearly proves that our del G function is continuous. So we have proved that it is a continuous group homomorphism from G to R cross. Now we will show that if our group G is compact, then this delta function is, if our group is compact, then this delta function is constant. Actually, this will be a very general proof, like it doesn't depend on delta. Basically, if we have any continuous group homomorphism from a compact group to R cross, then it will be constant. And the proof is very easy. Since G is compact, then the image of G under delta is also compact. In particular, it is bounded. Now we want to show that this is the trivial one map. If it is not trivial one, we can find a point which is not 1. And without loss of geometry, we can assume that it takes value greater than 1. Because if it is not greater than 1, we have delta of G times delta of G inverse equal to 1. If 1 is less than 1, another have to be greater than 1. So we can work with whichever G or G inverse, whichever image is greater than 1. Now we have delta of G power n is basically delta G whole power n. And this gets unbounded because the value of delta G is greater than 1. And this clearly shows that the image of delta is unbounded, which is a contradiction. So basically it shows that there is no group element for which delta of G is not equal to 1. So delta is basically a trivial map. So this clearly implies that from a definition of delta G is mu of Eg by mu of E. If our group is compact, then it means that mu of Eg equal to mu of E for every measurable E. This basically automatically implies that for compact groups, all left invariant Haar measures are also right invariant. Like for the counter examples, I don't have it in mind, but I think for the upper half plane in the complex plane, the upper half plane, it's a group. For it we have, like, I think there is some counter example. I don't remember it. Till now, is it clear? Okay. So for our rest of the talk, we'll assume G to be a compact group, unless we'll state otherwise in the statement. If nothing is stated, we'll assume our group to be compact. Again, for simplicity, we'll assume G to be also hausdorff. And in this case, we have a left and right invariant Haar measure mu on G, for which mu of G is less than infinity. Why it is less than infinity? Because Haar measure is finite, like I mean, we have a compact set, so the measure would be finite, obviously. So we'll normalize this measure to a probability measure. That is, you can divide the whole thing by the total measure to normalize it to 1. Basically, measure of the whole group will be 1 after the scaling. This is a pretty standard thing to do. So basically, this will give us a Hilbert space. Basically, a Hilbert space is basically a vector space, non-linear space, which is endowed with an inner product, and the norm is induced by that inner product, and it is basically the vector space is complete with respect to the norms induced from that inner product. Complete means complete as a metric space. It gives us rise to the Hilbert space L to G of square integrable functions on G. We have the inner product and norm in the usual way. That is, inner product of two two integrable functions f1 and f2 is basically f1g, f2g, dg. dg is basically d of mu of g, where mu is our Haar measure, but for our simplicity, we'll write it to be dg. And norm of f will be basically square root of f inner product of f comma f, this is also very easy to guess. So we'll try to make L to G, the square integral functions, into a representation of G. Again, you see, if you can make it a representation, this will be very important, because for any arbitrary compact group, we are making a representation. So this will help us to build a general theory. So one thing that we can ask is that for finite groups, we consider Kg like the regular representation. Why don't we consider that here? So the answer is that Cg, like the continuous functions of finite support on G, will clearly be a subset of L to G, but it's more convenient to work with L to G because particularly we'll do integration, and for integration, LP spaces are more natural to work with. So in this case, for compact groups, we'll call L to G to be a regular representation instead of C of G. Our C of G doesn't play a very big role for compact groups, because for compact groups, the integration plays the very major role, and for integration, like LP spaces are of most importance. So by a unitary representation, so for compact groups, see, in the previous case, we defined a representation of an arbitrary group to be just a vector space together with the action of the group. Now we are trying to define a representation of a compact group, or in general a topological group. So we have more structure, so that it's not an arbitrary group acting on the vector space. It's a group that has also some topology. We need to use that somehow. So basically, we can define a continuous representation. Basically, a representation is basically a group is acting on the vector space. Basically, each group element is acting as a linear operator on the vector space. If our group is a topological group, then for a continuous representation, in our definition, we'll require the operators that G induce to be also continuous operators on the vector space. This is more convenient. Otherwise, we will not be able to use the topology structure of the group G. So we need the represented matrices of G to be continuous linear maps on G. Again, for basically if we have finite dimensional representation, that is, if the vector space is finite dimensional, then all linear maps are continuous and have nothing to do. So basically, we work with Hilbert spaces where the things get more interesting. So by a unitary representation of a topological group G is a continuous group homomorphism from G to U of H. U of H is the group of all unitary operators on Hilbert space. Unitary means that are distance preserving. That is unitary matrices and unitary operators. Equipped with the strong operator topology. A strong operator topology means it's the coarsest topology on U of H, so that for each fixed vector x, the evaluation maps T goes to Tx are continuous in T. In a similar way, so we can basically for every object to respect all structures, we need to define what is the right things to study on that object. What are the right maps to define? What are the right structures to define? So we have figured that for for topological groups, the right object to study is basically continuous representations. But we'll focus more on unitary representations. That is, we require all our operators of G to be unitary operators rather than arbitrary continuous operators. The point is that because for compact groups, we see that all continuous operators become automatically unitary, so it is more convenient to work with them. Automatically unitary is not obvious, like whatever inner product we are given with, the group element might not be an unitary operator, but we can see that we can define another inner product on the edge with respect to that new inner product, all operators of G will be unitary, and we can without loss of unity work with that new inner product on edge, and we can do it for any Hilbert space. This is more convenient. It's more convenient to work with unitary representations rather than arbitrary continuous representations. We can work with continuous if our group is not like locally compact or any compact. In that case, we might need, but in this case, unitary representations are very convenient to work with. Since we have defined a new structure called unitary representation, we need to define our morphisms and other things accordingly. These are very analogous definitions. The morphism between two unitary representations is basically a morphism between those representations, and the morphism is a unitary operator on U. Basically, if you have a G and it acts on two Hilbert spaces H1 and H2, then basically a morphism between these two representations H1 and H2 will be a unitary G linear map from H1 to H2. This is what we mean, which respects all the structures. It is G linear, it respects the group action structure, it respects the group's topology because it's unitary. As an important note, if V rho is a representation of G, then the dual space V star also becomes a representation of G by the obvious way that we have defined earlier. In this case, the matrix of rho star G is a transpose of the matrix of rho of G inverse. In particular, if rho is unitary, then rho star G is just rho of G bar. Basically, for unitary representations, if we have like a matrix of rho of G, then the matrix of rho star of G is basically we're basically just taking conjugate on each slot. This is a very convenient thing for unitary representations that helps us to do a lot of calculations easily. So this is definition of unitary representation and morphisms between them. Are the definitions clear? Okay. So now which we'll want to do is try to define tau to be the representation of the, not representation, tau to be the action of the group G on the space L2G. Tau G will give us a representation. We're trying to make L2G into a representation of G. We'll try to do that in the following way. For every group element G, we have the operator tau G from L2G to L2G given any square integrable function f. We can define tau G of fx to be f of G inverse dot x. It's exactly how we defined our action of G on V star. Basically, f of rho of G inverse. It's a very similar, but in that case, we're doing it on any square integrable function. Tau G of f of x is also another function which should be also square integrable. It is f of G inverse dot x. It is easy to check that tau of G inverse is both inverse and adjoint to tau of G. It's just basically we just need to use the left invariance of the Haar measure. Straightforward computations. It's already a long talk. It has 41 slides. I cannot show all the calculations. So this will see it's adjoint means so it's unitary operator, and unitary operators in particular bounded. So we get a homomorphism tau from G to the group of unitary operators on L to G. That is, G is going to the operator tau of G, basically representing each group element by a unitary operator tau G on L to G. We'll show that this is a continuous homomorphism. Otherwise, if it is not a continuous homomorphism, then L to G won't be a unitary representation. It will be just an ordinary representation as for ordinary groups, not topological groups. So we'll try to prove a general lemma first, that is, space of all compactly supported continuous functions on G, CCG, is dense in L to G, or in particular in LPG for all p greater than equal to 1. So these are standard tricks from measure theory. We'll try to show that any simple function, that is linear combination of indicator functions can be approximated by continuous functions in L to G. It is enough to work with not simple functions. It is enough to approximate any indicator function by continuous function. The linear combination will follow very similarly, and for any arbitrary function, it's integrable function, we can just use sequence of simple functions and the monotone convergence theorem stuff, the standard measure theory things. So we pick any a with mu of a less than infinity. We'll try to show that the indicator function of a can be approximated well by such continuous compactly supported functions. So by inner and outer regularity, that is by approximation from above and below by open and compact sets, there is an open set U and a compact set K, so that we can mu of U difference K is less than epsilon. Now since G is compact hausdorff, it is also normal by Urysohn's lemma. So this is a famous lemma from topology, Urysohn's lemma, which says that if you have a compact hausdorff topological space, then basically you can separate points by continuous functions. Separate disjoint closed sets by continuous functions. That is, given, suppose you have a compact hausdorff topological space X and you have two disjoint closed subsets A and B. Then you can construct a continuous function f from this X to 0 so that f is exactly 1 on A and exactly 0 on B. Basically, you can separate A and B by that continuous function. We'll use that here. So basically, K is contained inside U. So K is a compact set, so it is particularly closed because G is hausdorff. Here we are using G is hausdorff, and K and U complement are disjoint closed sets. So by Urysohn's lemma, we can find a continuous function which is 1 on K and 0 on U complement. Then both indicator and F agree on K and U complement. So basically, you can directly say that the difference mod of 1A minus F is only non-zero on U difference K. And we can difference. So now we can just like estimate the norm of the difference between like the indicator and the continuous function in the following way. It is U difference K mod of 1A minus F whole square dg. And it is bounded by some measure of U difference K, some constant. Why? Because the function 1A and minus F whole square, this is also bounded. Because the indicator function of it takes values 0 and 1, F is also bounded. So their difference whole square is also bounded. So we can, if we bound it by M, then it is basically less than M times measure of the set U difference K. And we have already found it to be less than epsilon by construction. So I'll leave the proof here because we're already done. We have basically approximated indicator functions, then we'll approximate sum of indicator functions in a similar way, and then we'll use limits and monotone convergence theorem to get the general thing, which is like very standard. I'll not prove the rest. So I'll try to proceed further. I'll use this fact that is given any square integral functions, you can approximate it very nicely by continuous and compactly supported functions. We'll use it to prove that the representation tau g, this is a continuous, that is a continuous representation. The map tau from G to U to G is continuous because of we have endowed U L to G with strong operator topology. We need to show that all evaluation maps are continuous. So it is enough to show that for each fixed square integrable function f, the map G to L to G given by G goes to tau G times f is continuous. That is, G goes to f of G inverse x is continuous. This is how we define our tau G, f of G inverse x. So by the previous proposition, we can choose a phi so that a continuous compactly supported function phi so that it is very close to f, say epsilon close. Now since G is compact and phi is continuous, any continuous function on a compact set is uniformly continuous. Again, uniformly continuity is generally meant for metric spaces. G is not a metric space in general, but there's something called uniform spaces, and we can define a very general setup of uniform continuity on that spaces. I'll not go into the detail, but this is what we mean by uniform continuity on topological groups. For So basically, to be epsilon close, we can have an open set U, so that if G1 inverse G2 is in U, then phi of G1 inverse and phi 2 of G2 inverse are very close to each other. Close to each other. If it was not uniformly continuous, this we have needed to fix one of G1 or G2, and this U would be dependent on some G1 of G2. Because of uniform continuity, for this epsilon, this U only depends on epsilon. This is what we mean. This U doesn't depend on any choice of G1 and G2. It only depends on epsilon. Now we use that tau G is an isometry. Why? Because tau G is an unitary operator. Unitary operators are isometries. We get that tau Gn of f minus tau d of f. Its norm can be easily approximated by our usual triangle inequality, and we use our isometry here. Basically, tau Gn of f minus tau Gn of phi is basically more norm of f minus phi, because tau Gn is an isometry. And we only need to approximate this second quantity. And basically phi is where G is not fixed, so it is basically this second quantity is clearly less than sup of mod of phi on Gn inverse G minus phi of G2 inverse G. We are using our definition of tau up here. Tau Gn of phi is basically phi of G1 inverse applied at our argument. And this is our definition of norm. And this supremum is less than epsilon by our uniform continuity, and the norm of f minus phi is already less than epsilon by our choice of phi. So this shows that the map tau G to L, U of L to G, the group of unitary operators on L to G, is continuous. That is, we have already made L to G, the square integrable functions of G, a representation of the group G, a continuous representation. It is also unitary because we have already seen that, I mean, not proven, but it's easy to prove that all operators tau G are unitary. We'll try to see how this thing L to G, how this representation L to G behaves. For finite groups, how does the group algebra KG behaves was of utmost importance. In that case, we have studied that thing very deeply. For compact groups, we will study this L to G very deeply. So for our purposes, the regular representation L to G is very big to work with, because L to G is, of course, infinitely dimensional. It is super big, you know. Like L to G already contains C of G, that is all continuous function from G to C with finite support, so on. And C of G has basis G. Basically, in particular, for any group G and for any field K, the group algebra KG has basis G, because the elements are formal linear combinations K dot G, right? And basically 1 dot G, this forms a basis, and 1 dot G means you can identify it with G. So the whole group G becomes a basis of KG. In our case, whole group G will become a basis for CG. And for most locally compact groups, they are mainly uncountable, because we'll be mainly working with like group of unitary matrices or orthogonal matrices or R power and C power and so on. They're clearly uncountable. So we have L to G has a subspace CG which has an uncountable basis. So it is usually infinite and like it's very big. So it is not very convenient to work with it alone. So we'll try to break it into direct sum of simpler subrepresentations. This is what our target is. And we'll try to see how it decomposes. This is our like a general philosophy of representation theory. You take a big representation and you try to like make a general theory, build a general theory on how that big representation decomposes, what are the multiplicities and so on. So we want to find smaller representations by locating left invariant closed subspaces of L to G. Left invariant is again important because we need to respect the group action structure. Closed subspaces, why are we looking for closed subspaces? For it is very convenient because you can apply spectral theorem and a lot of things. For finite dimensional vector spaces, all subspaces were closed, but this is not true for infinite dimensional vector spaces. So here we need to pay special attention to closed subspaces, and we'll try to study them with the property that tau G of V is subspace of V for every G. I mean, it has to be stable, otherwise we will not be able to get a subrepresentation. Then the restriction of tau to V becomes a representation to the unitary group of V. In particular, if V has some finite dimension n, then we can identify V with C power n, and basically U of V can be represent identified the unitary group Un of C. That is all n cross n unitary matrices. Basically, it will give us a homomorphism from G to Un of C. This is what this is basically what we want to do. We can now let's try to see how we can find these subspaces. Like we want to identify small finite dimensional subspaces of L to G. For this, we'll need to define, like we need to build more tools, which we'll do now. So we can find these close invariant subspaces by constructing. There are many ways to do that. Well, I'll show one construction by constructing self-adjoint operators on L to G, which are also morphisms. Being morphism is very important because otherwise kernel image and eigenspaces they may not be like invariant under the action of the group. I mean, they may not be sub-representations. So basically, so we'll try to work with kernels and eigenspaces of this morphism that are also self-adjoint operators. So in analysis or in like Fourier analysis, like convolution is a very common thing to do, even in analytic number theory and so on. So given two square interval functions, we can define their convolution to be the following function. F1 star F2 of x is integral over G, F1 G, F2 of G inverse x dg. This is for locally compact group G. For R or C, many of you have seen this definition, integration of F1 t times F2 of x minus t dt. In that case, minus was a group operation, like additive group. In this case, it's something general, but it's still not difficult to guess. One nice thing is that this function always becomes continuous. Like I think not in every case, but for real numbers, one thing I remember that even like they have only integral functions, then their convolution always becomes continuous or something. Like convolutions like are very nice. They behave very nicely. Using this convolution, we will try to construct a self-adjoint operator, which is a morphism on L2E. This is our next target. Is this clear till now? Okay. For each phi in L to G, we can define the right convolution operator by just convoluting by S. I mean, for each phi, we can just take any function and take its convolution with phi from the right. This will call to be the right convolution operator. Then by Cauchy-Squartz inequality, it's obvious that T phi is a bounded linear operator because it will in particularly bounded by, we'll use the Cauchy-Squartz inequality here. So it will be bounded by norm of f times norm of phi. If phi satisfies some nice conditions, that is, phi is just a function, but if it behaves like in sort of a unitary fashion, that is phi of G inverse equal to phi G bar, then we can show that T phi will be self-adjoint, which we can be easily proved by Fubini's theorem. Basically, we just need to we need to check the inner products, which will be like T phi is also defined for an integral and inner product is also an integral. So we'll get a double integral and we just need to change the order and Fubini's theorem will justify it. It's again a straightforward computation. And for basically we have Haar method. The most thing that we can do is by left multiplication or right multiplication. We don't know anything that we can do. This is the only thing that we can do. Similarly, we can show that T phi is an operator. So the lambda eigenspace V lambda of T phi is a left invariant, a close invariant subspace of L to G. And again, we can prove it by a very simple substitution in the integration and left invariance of Haar measure. So we can see that for all nice quadruple functions phi in L to G, we can construct many like right convolution operators, different convolution operators, and this will give us a lot of different closed invariant subspaces. We can generate a large number of subrepresentation of L to G using these operators. Now our next goal will be to apply the spectral theorem, the Hilbert-Smith spectral theorem, to this type of operators, which we'll discuss in the next slide. By a compact operator on a Hilbert space, we mean a linear operator T from X to H such that if we have a bounded set, then its closure of its image is also compact. We typically these sets, we call them to be pre-compact sets. But we'll not use a lot of different terminology here, we'll just write it as it is. In particular, if we have an unit ball, then its image closure will be compact. So for finite dimensional, it is obvious because in finite dimension, unit ball was compact, but in infinite dimension, unit ball is not compact. So its image is also, it might be unbounded, it can have many bad things. So in finite dimension, all operators were compact. In infinite dimension, it is not the case. So this type of operators get a lot of special attention. The good thing is that image of unit balls under this thing is compact, and I mean the closure of the image balls are compact, and in particular they are bounded. So basically they attain maximum value, and we can define operator norm for these functions. For arbitrary operators, arbitrary operators on Hilbert spaces, we cannot define operator norm. But for compact operators, we can define operator norm, and many nice operator norm properties we can use, and we can prove a lot of results in analogous way that we did for finite dimensions. So here is the spectral theorem for self-adjoint compact operators. This is called the Hilbert-Smith spectral theorem. We can show that for any, if T is a self-adjoint compact operator in a complex Hilbert space H, then for if we lambda, like if we have lambda i's to be the eigenvalues of T, then we can show that summation lambda I square converges. In particular, lambda 1, lambda 2, this sequence basically converges to 0. Otherwise, I mean, it will not converge. So we can just order then according to a norm, and it will go to 0. So there is a countable sequence lambda 1, lambda 2 of non-zero reals, so that we can decompose the Hilbert space H as direct sum of the eigenspaces of the operator. Or in particular, T is diagonalizable, whatever you can say. Basically, no, not really. I think whatever. So here lambda in are eigenvalues of G, and as n goes to infinity, this lambda n's go to 0. This is spectral theorem for compact self-adjoint operators. This statement is not very difficult to understand, so I'll move to the next slide. So we can apply the previous theorem to T phi to conclude that L to G is a countable direct sum of finite dimensional unitary subrepresentations. However, in the previous theorem, we need T to be compact self-adjoint operator. T phi was self-adjoint, it was easy to see, but the fact that T phi is compact is not that obvious. So we will justify it by a general fact from measure theory. So we want to show that the map T phi is a compact operator. So let X mu and Y mu be sigma finite measure spaces. That is, it's countable union, like both X and Y are countable union of subspaces, and each part has finite measure. This is what we call sigma finite. Let K to be an integrable function on X cross Y with the product measure mu cross V. We define an integral operator T in the following way. T of f of y is basically integral along x, k of xy, fx and d mu x. If this k is called the kernel of this type of operators are called Hilbert-Smith operators, and this k is called kernel of that operator. I mean, this type of things are pretty, these are widely studied in function analysis. And T is a compact linear operator. I don't know, I haven't tried this proof yet. I directly quoted this fact. So now choosing T to be T phi and K to be our phi of X inverse Y, it shows that T phi is an integral operator and hence it is compact. So here is the fact that phi in the previous slide where we defined phi, we needed phi to be L2G. Why did we need phi to be in L2G? We needed F to be bounded. T phi to be bounded. That is, we needed to apply the Cauchy squares inequality. In that case, phi being square integral was not necessary. Like to show that T phi is bounded. It is necessary to show that T phi is compact. Otherwise, if phi is not square integrable, this K might not be in square integral in the product group G cross G. We haven't even this particularly works for compact groups. Like if G is locally compact, then you can show that there are T phi's that are not compact. Even for G to be R, the real numbers. Like in Terence-Chaw's block, there was one of the exercises where it was to show that an integral operator on real numbers is not compact. So we cannot extend it directly to locally compact groups. Being compact is very important here. Haar measure we can define on locally compact groups, but to develop all this theory, compactness is particularly very important. Many things do not generalize on locally compact groups. Now here is one thing. So we have write our Hilbert space as P naught dx sum of lambda eigenspaces. In this case, or for a T phi, H was L2G. So here is one fundamental question. We have to pick a particular fixed eigenspace. So here all these things might not be distinct, they might be same, like it can have multiplicities. So pick a particular eigenspace. What can we say about how many times that eigenspace appears? Finite, countable, uncountable. If finite, how many times? This is a fundamental question. This is one part of the statement of the Peter Weyl theorem. We'll go there shortly. When this is the second part of the Peter Weyl theorem, we'll do that at the end of this lecture, near the end. But let's move on. So a matrix coefficient of a representation is a function of the form eta of rho g of v, where v is a vector, eta is a continuous linear functional. So given a representation, a matrix coefficient is obtained from two data. We need a fixed vector and a continuous linear functional on it. In particular, for Hilbert spaces, we can apply the Riesz representation theorem to show that any linear functional is inner product with some vector. So they look like this one. Here is one definition for a fixed representation rho. We write eta rho to be a set of all matrix coefficients of G coming from the representation rho. A matrix coefficient depends on a representation. It depends on representation, a choice of a vector, and choice of a linear functional. Then we define eta to be the set of all matrix coefficients of G coming from all finite dimensional representations. All finite dimensional representations. So why do we call them matrix coefficients? We'll see a short example in the next slide. If J is a finite group, then we fix a basis and fix a dual basis. Then for a representation of finite group, what we do? We represent each group element by a matrix. So the matrix entries depends on the group. So we can think the entries, we can think this as functions on the group. These functions, these entry functions, they are basically the matrix coefficients. In particular, basically, from the Riesz representation theorem, F, C, W, G's are all matrix coefficients. We can basically take V to be like VW to be like the orthogonal basis vectors, and this will do our job. We can use that rows are unitary operators in most of the cases. For finite groups, we can just take V to be I, W to be EJ, and it will give us the ith and jth slot of this thing. That is, G goes to rho I j of G is our matrix coefficient. So here is a thing for any group G, set of all matrix coefficients. That is, we are varying over V and rho and take their linear combinations, but we are also varying over rho. For eta rho, the matrix coefficients, the rho was fixed. We are taking coefficients from a particular representation. That is, if we take up, let's say, 7-dimensional representation, we are representing each group element by 7 cross 7 matrices. In that cases, we will get 49 entries for each matrix, and this will give us 49 functions. So these 49 functions will come from a particular representation. This is what we mean by eta rho for that particular 7-dimensional representation rho. For eta, we consider matrix coefficients from all possible representations, finite dimensional. Here is a lemma. It shows that set of all matrix coefficients from a self-adjoint subalgebra. of algebra of all continuous functions on G. Why are we proving this? Because for one of the statements of the Peter Weyl theorem, we'll use the Stone versus theorem. And if you know the statement of Stone versus, then like self-adjoint, these stuffs are very, we need to prove these things. So we'll prove this in here now. So take any two matrix coefficients f1 and f2 and any complex scalar lambda. And lambda f1 is basically just multiply the linear functional eta by lambda. This will give you lambda times f1. So if f1 is a matrix coefficient, lambda times f1 is also a matrix coefficient. If f1 and f2 are matrix coefficients, then f1 plus f2 is also a matrix coefficient. How? So f1, how do we obtain f1? F1 is obtained from one representation and one. So how do we find a matrix coefficient? We need one representation row, one vector, and one linear functional. If we have f1 and f2, that is, we have two representations, two vectors, and two linear functionals. We can show that f1 plus f2 is obtained by the representation rho 1 direct sum rho 2 with the choice vectors v1, v2, and the eta prime is basically the linear functional which is takes vw to eta1 v plus eta2 of w. It shows that if f1 and f2 appear as matrix coefficients, then f1 plus f2 also appears as a matrix coefficients. It comes from the respective direct sum of the representations. Similarly, f1 times f2, because you want to show that it's a self-adjoint subalgebra, it also needs to be closed under multiplication. Similarly, f1 times f2 appears from the tensor product. And to show self-adjointness, we need to show that f1 bar is also in a matrix coefficient. It will come from the dual. Why? Let's go back to a few slides before. I think, yeah. So if rho is unitary, then rho star G is just rho G bar. So for unitary operators, basically the dual representation is same as like basically conjugating. And for if I have like linear functional, then the dual representation will basically same as conjugating the function. In representation theory, this is very common. There is something called characters which we will not discuss in this talk, but they are pretty important. Basically, in representation theory, this is very common. Like sum comes from direct sum, product comes from tensor product, and conjugation comes from dual. I mean, this is, you can just take it as a slogan or something. So now we can move to the first version of the Peter Weyl theorem. We have developed all the necessary background. Can I move now? Okay. Let G to be any compact Hausdorff group. Wait. Okay, fine. Let G to be a compact Hausdorff group, then our first statement is that there are sufficiently many finite dimensional representations to separate the points of G. That is, when for any two different points x and y in G, there is a suitable representation rho such that rho x not equal to rho y. That is, we can separate the points in G by different representations. We can, that is, given any two distinct points, we can find a representation that is the way the x and y are represented as matrices, they are not same matrices. The second statement is that the set of all matrix coefficient is tensed in CG, that is all continuous functions on G. So let us try to prove the first statement. The second statement will easily follow from the first statement together with the previous fact that the self-adjoint algebra thing. We'll apply Stone versus for the second statement. For the first statements, because of the group homomorphism property and rho is itself a homomorphism, is enough to find a rho show that rho of x is not same as rho of 1. And rho of 1 is the identity because it's a group homomorphism. One should go to identity. If the identity element must act as the identity operator. Now we don't have many well-known representations of G, so we'll try to build something from a regular representation L to G. We have seen that for a suitable phi, the operator T phi is self-adjoint and compact. and its eigenspaces form an orthogonal direct sum of L to G. This is from the spectral theorem, and they're all G invariant because they're eigenspaces of G linear morphisms. So restricting the regular representation to each such eigenspace V lambda gives us a subrepresentation. We'll find a finite dimensional invariant subspace of L to G on which tau x doesn't access identity. This will prove this. Suppose this is not the case, then it will mean that tau x minus identity, tau x acts as identity on every finite dimensional subspaces of L to G. That is tau x minus identity map. This basically acts as the zero operator on each eigenspaces and thus on L to G, because basically L to G is direct sum of V lambdas, and this tau x minus I, it acts on zero on each copy, then it will also act as zero map on their directs. Basically tau x minus I acts as zero operator on the whole of L to G. Now since Tg commutes with tau, Tg commutes with tau because Tg is a morphism and tau is a representation. Morphism, G linear morphism means it respects the representation structure. Basically it commutes with the representation operator. And in our case, our representation operator is tau, and G is our function. So it means that tau G applied at tau x minus I of f is 0, because tau x minus I itself the zero map. It directly implies that tau x of f star G, because this is how we define that our map Tg. Tg of f is f star G. So tau x of f star G is same as f star G. And if we have unravel the definition of tau x, it just means that if convolution G applied at x inverse y is same as f convolution G at y. This is what we have obtained assuming the contradictory statement, that is tau x minus I annihilates each subspace. We want to arrive to a contradiction, so we want to show that this equation f star G is same as if star G takes value at y is same as f star G taking value at x inverse y. You will show that this is not true always. We'll try to construct a counterexample. So we'll try to construct f and g so that f star G is non-zero at 1 and vanishing at x. We'll basically take y to be 1, and this will give us our contradiction. So we choose an open neighborhood u around 1, the identity element, so that x is not in u square. So basically x is not same as 1 and x is not in u square, but here we are using a hausdorffness of our group G. So we can replace u with u intersection u inverse to without loss of assume that u equal to u inverse. Like we're shrinking u to a smaller open set so that it becomes a symmetric neighborhood. This is very common technique for topological groups in general, not for any compact group. I mean in any topological group. We can take our f and g to be the indicator functions on u. One can easily check that f star g takes value 1 at it takes value mu of u to be at 1, and mu of is positive because Haar measure is positive on every open set. We have proved it already before. By our definition, I mean on every open set. So mu of u is positive, and f star g at x is same as mu of u intersection x mu. That is mu intersection with translate of mu by x. And this is empty because x is not in u square. With the condition that x is not in u square, same as saying u intersection SU is disjoint. When u and xu are disjoint. You can again check it easily by hand. We need to use that u is a symmetric neighborhood. So basically inverse can also interchange inverses, but this is straightforward to check. So basically f star g takes 0 value at x and a positive value at 1. This clearly contradicts our initial statement that f star g takes value, f star g is value at x inverse y and y are same for every y. And this contradiction shows that our initial statement was wrong, that is tau x minus identity cannot act as zero operator on every v lambda. So there is some eigenspace v lambda on which tau x minus I doesn't act as zero operator. That means there is on some eigenspace tau does not act as the trivial operator. And this proves our first statement. For our second statement, we'll show that the set of all matrix coefficients is dense in C of G. Let's try to see what we have obtained till now. Let's recall our statement of Stone-Weierstrass. It says that given any self-adjoint subalgebra of the continuous functions that separates points and that is non-vanishing, then that algebra is dense in the whole algebra of all continuous functions. Separate points means given any two distinct points x and y, you can find a function f on that algebra so that f of x is not equal to f of y. And non-vanishing means all functions cannot vanish at a single point. That is, for every point x, there is a function f so that f of x is non-zero. You need to check only these two things. The self-adjoint algebra part is already done. The non-vanishing part is also not non-vanishing. The separating points part is almost done. Only need to take care about the non-vanishing thing. That will also be very easy to see. We'll see. So for the proof of two, using Stone-Weierstrass. So for the general statement, as a note, for the general statement of Stone-Weierstrass, we don't need our space to be like compact hausdorff. We can relax our condition to be locally compact hausdorff also. But again, like the operators are PGS, like self-adjoint compact, for these things, compactness are necessary. We can relax our compactness to locally compact in many cases, but there are many cases where the compactness required condition is very strict. So let's move to the proof. We need to show that eta separates points. Note that from the first part, we have already found a finite dimensional eigenspace of V lambda so that rho x is not equal to rho y on V lambda. That is, rho is not identity on V lambda. So there exists phi in V lambda so that rho x phi is not same as y of phi. Since the vectors are different, we can find a suitable, by choosing a convenient like dual basis, you can find a linear functional which takes different value on these two different vectors. That is, we can find a linear functional L so that L applied at rho x at v is not same as L applied at rho y at g. If we define our lambda of g to be this L of rho g of v, then it is clearly a matrix coefficient by our definition, because what do we need for a matrix coefficient? A vector, a representation, and a linear function. We have obtained the three things and it's exactly in the same form. So it is a linear function, it is a matrix coefficient, and it's clearly its value and x and y are not same by your definition. So you have shown that it separates points. Now you need to show that it is non-vanishing. That is, given any point on the group, we need to find a matrix coefficient that doesn't vanish on that point. And this is trivial because the constant function 1 is in our matrix coefficient. Why? Because trivial representation. Its matrix is given by the identity matrix. Its entries are 0 and 1. So the constant 1 function is already a matrix coefficient, which is coming from the trivial representation. So it clearly separates points, and we are done. Is the proof clear? Okay. So let's recall the statement that the first statement is not very important. It is part of the theorem, but it's mainly to prove the second theorem. And second theorem is very important. That is, set of all matrix coefficients is dense in the group of all continuous functions on G. I mean the algebra of all continuous functions on G, not the group, sorry. So here it's a nice consequence. So for finite groups, we had a theorem called, like, I forgot the name, Cayley's theorem, sorry. It says that any finite group can be embedded in some sufficiently large symmetric group. And we can be more particular. If our size of the group G is n, then we can say that we can embed G inside Sn. And by left, because the left multiplication operation on G acts as permutation. We'll develop here we are giving a very similar theorem for compact groups. So for a compact hausdorff group, take any neighborhood around the identity element. There exists a compact normal subgroup H contained in that neighborhood so that we can lose a small amount of information from that group. that is, we quotient out by H, the resulting thing, G mod H, we can embed it inside a general linear group. That is, G mod H is isomorphic to a closed subgroup of a general linear group. In particular, it will be like isomorphic to a compact subgroup of a general linear group because G mod H is compact. Like if we mod out a compact group by a closed subgroup, the resulting thing will be like quotient of compact spaces are compact. An image of isomorphic means a continuous homomorphism, so image of G mod H will be also compact because it's image of a compact set and the continuous whatever. So let's move to the proof. Since U is open, G differs here, that is G intersection U complement is a compact subgroup of G. Though subspace of a compact space is compact. Pick any G in the G difference U. By the previous theorem, we can find a finite dimensional invariant subspace Vg of L to G so that tau G acts non-trivially on Vg. Now we can identify Vg with C power Ng for some integer Ng because Vg is finite dimensional. Thus restricting the action of tau on Vg gives us a continuous group homomorphism from G to GLNG of C. In particular, we can take GLNG to be like ULNG also, like the unitary matrices, but we haven't shown that all continuous representations are unitary. After we prove that, then we can like embed it also inside UN of C also. But I mean, in this case, we can just move on with this. Like the proof will be very similar. So basically, we have using the previous theorem, that is, we can separate points by the representation. We have seen that after finding the closed invariant subspace of finite dimension, we can, for each group element G, we can find a representation, continuous representation of G, which doesn't act as identity element on G. And this is we have obtained for every group element G on G difference U. Now Vg was a neighborhood of G, and G was varying over G difference U. Now basically they covered this open space Vg covered all of G difference U. Since G difference U is compact, we can cover it by finitely many VGIs, say V1 up to Vk, so that the corresponding restricted representations rho I G to GLNIC, we have the following statement: for each G in G difference U, at least one of rho 1 G up to rho kg is non-identity. Why? Because like rho 1 G is not identity on V1, rho up to rho kg is non-identity on Vk, and G difference is contained in V1 up to Vk. Basically, for every G in G difference U, it is in some Vk, and on that Vk it will not be identity. So we have the following statement: for each G in G difference U, at least one of the rho 1 G up to rho kg is non-identity. Now if we form the direct sum of the maps, like direct sum of the direct sum of the representations from G to the direct sum of GLNIC, and by the usual embedding, like GL1C plus direct sum GL2C can be embedded inside GL3C, and like this is a standard embedding. By taking block matrices, direct sum of GLNIC can be easily seen as a like subset of GL N1 cross up to NP of C. By taking block matrices, you have an N1 cross N1 block matrix, and you have an N1 cross N1 matrix. You have N1 N2 cross N2 matrix. You can form a block matrix of size of N1 plus N2 by taking the block diagonal or thing. It's a standard thing. So we have found a representative of G inside GL of N1 dot plus dot dot NK of C. Then there was still continuous homomorphism because you have direct sum of continuous maps is clearly direct, is continuous, which is again non-trivial. Why? Because it is component wise and we have many components, and for each G in G difference we have seen that at least one of the components is not identity, so the whole resulted thing will be also non-identity. It's still non-identity for any G difference U. That means for it is identity, it must not intersect G difference U. So the representation rho where it is acts trivially, it must be inside U because it cannot cut G difference U. So the kernel of the representation is a closed subgroup of G, so it's clearly compact because closed subgroup of compact is compact and it is contained inside U. So the H is our kernel, and G mod H can be like embedded inside. G mod H can be like by our first isomorphism theorem or whatever, G mod H can be realized as a subgroup of GL N1 plus dot or NK of C, where H is the kernel of the representation. And this proves our theorem. Now, in the previous thing, like basically this N, the whatever general linear group N we get, we cannot directly construct it from the information from the G, because we're taking open covers and we're taking a lot of open, like local data to get the global data. So for finite groups, for the Cayley's theorem, the in which symmetric group we can embed was pretty obvious. But in this case, we cannot say the obvious integer. Like they clearly depend a lot on local data. We cannot say anything. I mean, as far as I know. So the next part of the talk is to prove the second part of the Peter Weyl theorem. That is the multiplicity question. Like how many times a particular simple part occurs. So we need to develop some more theory for that. So here is the thing. That is, this is why I said that any continuous representation can be thought as a unitary representation for compact groups. Here is a statement. For any continuous representation rho, okay. For any continuous representation rho of the compact group, we can construct a G invariant inner product on H. That is, H was already a Hilbert space. It has some inner product. But using our group action on H and our Haar measure thing, we can construct another inner product from that inner product, which will be automatically G invariant. And G invariant inner product, it means that all our group element operator rows that will be unitary operators by definition. This is why for compact groups, we can by default assume that all continuous representations, finite dimension, are unitary. Because if they are not, we can just whatever inner product we have on our vector space, you can just replace it with our G invariant inner product. We can work with that. So this is our process. Again, this averaging, this is very common thing in representation theory. So given any inner product, we have the action of G and we have the Haar measure. We can define new inner product by averaging. That is, the inner product induced by the representation rho is take all G dot V and G dot W and integrate it over G. Again, for finite groups, we could have given a proof of the Maschke's theorem using a similar way by giving a G invariant inner product. In that case, what would we do? We take VW rho to be 1 by size of the group times summation of G dot V comma G dot W. That would be our case. In which case our group was finite and the Haar measure would be a counting measure. And 1 by size of the group will be just a normalizing factor. That's it. And again, easy to check that G dot V and G dot W and like the inner product, basically just says that the actions of G, like the dot G map, that like the map how G acts are isometric, basically unitary maps. I mean, it directly follows from definition. But because you're integrating, if here you're integrating with the variable G, so let's take any HV comma HW, basically G dot H dot V, H dot W. But again, multiplication by H is a homeomorphism. You can replace GH equal to U and DG will be something by left inference, the measure will not change, and we'll get this identity of the inner product. This is easy to prove. I'm not proving it. The upshot is that we can always work with a G invariant inner products. We can assume that all group elements acts as unitary operators, given that they are continuous. Here is our Maschke's theorem's analog for compact groups. For any compact group, the finite dimensional unitary representations are semi-simple. I mean direct sum of simple unitary representations. The proof is also very simple. If we have a G invariant inner product on G, then any unitary subrepresentation, its complement also becomes, complement means the orthogonal complement, the perp space. It also becomes a unitary subrepresentation of the group. Why? I mean, we can using the G invariance, you can easily check that. I'll not show the simple calculations, the details. I mean, I don't have that much time. So the upshot is that given any invariance it will not hold for any inner product. The G invariance is very important. So on the Hilbert space, if our inner product is not G invariant, we will just average to make it G invariant. We will work with that. The advantage is that given any sub-representation, its orthogonal component also becomes invariant. Now, for finite dimensional representation, we can proceed inductively. If V is itself simple, we're already done, nothing to prove. If V has a unitary sub-representation W, then by the above discussion, we break as W direct sum W prop as unitary sub-representations. If our inner product was not G-invariant, this V equal to W direct sum W prop would anyway hold as vector spaces, but in this case, W prop would not be a unitary sub-representation. And in that case, this decomposition will not hold as representations. It will hold as only ordinary vector spaces. We have less structure. We have lost some structure. G invariance helps us to keep our structure intact. We can inductively do that. If W and W purpose both simple, we'll stop at this step. We are done. If one of them is not simple, it has some subpart, let's say U, then we can write W as U direct sum U prime. It will just go on forever. But we cannot go on forever because we have finite dimension. It will stop somewhere and will be done. This is the proof. We have given a proof for Marshke's theorem for finite dimensional case, but the same proof will work for Marshke's theorem. So this inner product approach proof will also work exactly for Marshke's theorem for finite group case. In that case, like by the counting measure, we can define we can average over, take a discrete average to make a G invariant inner product for the finite group, and we can do the exact same proof we did here. This inductively way to break up. The exact same thing will work. So can I move? Okay. So this Groot's lemma is common in all parts of representation theory. Representation of groups, representations of algebras, Lie algebras. This is in fact for any semi-simple modules. Basically, if you have like two simple structures and a structure preserving map between them, then it is either zero and isomorphism. It's very simple, the proof. The idea is that it's if I have a structure preserving map, then its kernel and image are both substructures. But because its domain and codomain are both simple objects, then the kernel has to be either zero or the whole of the domain. And similarly, by simplicity, the image also has to be either zero or full codomain. And by analyzing all cases, you can see that only possibilities are either it's an isomorphism, in which case the kernel is zero, or it is just a zero map, either zero or an isomorphism. This is what Groot's lemma says. In our cases, we don't have only algebraic structure, we have a continuum, we have a topology on it. So we need to be a little bit more careful. So we note that kernel T is closed invariant subspace, so it is either zero and isomorphism. And it clearly follows that T is either zero and isomorphism. Now, in representation theory, we work with arbitrary fields, and if our field is not here we can also say something more, that T must be a scalar multiple of the identity map. Any like structure preserving map, any G linear map between two simple representations. So if you work over arbitrary field of arbitrary characteristic, we might not be able to tell this. We can tell that T is zero and isomorphism, that is clear, that holds in general, but it being a multiple of identity, it may not be true. For that, we need an algebraically closed field. In either cases, you're working with complex numbers, so here it doesn't matter. But we'll do if H equal to H prime, then the identity map makes sense. Now, because of algebraically closure, we have eigenvalues of T inside. It means that T minus lambda I is not an invertible G linear map. So by the first part, T minus lambda I is either zero or an isomorphism. It is not invertible means it cannot be an isomorphism, so it must be zero. That's it. It means that for between a same simple unitary representation, all G invariant maps are just basically scalar multiples of the identity map. So basically, dimension of home G H comma H prime is just one. All scalar multiples of a particular vector, which is the identity matrix or whatever. So here is a nice corollary. If H is a unitary representation of a group G, of our compact group G, then for any two simple unitary representations, V and W, then either they're isomorphic or they're perpendicular. The proof is also simple. Take just a projection map from the big Hilbert space to the W. and restrict it to V. It is G linear morphism. So by Spruce lemma, it is either 0 or an isomorphism. If it is an isomorphism, it will directly give us an isomorphism from V to W. If it is 0, it will directly mean that V is perpendicular to W. And that's the proof. This Spruce lemma is a very simple thing, but it has a wide number of applications. After Spruce lemma, a most important thing that appears is Spur orthogonality relations. I'm not writing the whole thing. I'm not writing it in its more simplified form because I haven't introduced characters. In this talk, we don't need characters, so I'm not introducing it. So for a finite group case, we recall our averaging map. Given any T linear map T from V to W, we can average over T to get a G linear map TG, as we did before. That's treating our home GVW as a vector space and take the averaging map to its fixed subspace. This is our G linear map TGV. In our compact case, we can do a very similar thing. To continuous representations of a compact group, for any bounded linear map A from 0 to V pi to 0, the map AGV we can replace by similarly. The 1 by size of G will not be there because we have already normalized it to 1. G dot T of G inverse dot V. For continuous representations, we usually don't write to like dot, we try to like the operators as rho pi as representation. So G dot T will be like some rho G of T. T is basically A here. We're just mimicking the formula. The same thing will work here. This is why at the beginning I mean that like the 1 by size of the group times summation over G variation of G, it will serve analogous to the integration. The same thing will work here. Given any bounded linear map, we can integrate over the group, integrate the map over the group to make it G linear. So here is the Spur orthogonality relations. V rho and V pi are non-isomorphic irreducible representations of the group G with G infinite inner products. Even if they are not G infinite, we can average to get a G infinite inner product. It doesn't matter. Then for AV in V rho and BW in V pi, then the corresponding matrix coefficients are orthogonal. In other words, any two matrix coefficients coming from two non-isomorphic irreducible representations are orthogonal in L2G. This is what we mean. And these are Spur orthogonality relations. And even if they're coming from same representation, they will still be this matrix coefficient will still be orthogonal unless they are the same coefficient. We can show that the same coefficients are orthonormal. I mean, they have norm 1. I'm not writing everything. I'll not get much time. So for a proof, we'll again use Spur's lemma in a clever way. We'll define a linear map A from 0 to V pi by A of V to be the inner product of V comma B with times A. And this inner product is with respect to pi, the rho pi. The G invariant inner product on V pi. Now the integral on the above, this integral that I want to make it 0, it is nothing but the inner product of AGW comma V with respect to the G invariant inner product with respect to rho. This you can easily do because you can distribute the integration over inner product and you can justify by Fubini's theorem. Like AG rho will give one integration that like inner product will give another integration. These two integrations we can interchange order. It's easy to prove. Now, since V pi and V are non-isomorphic representations, we clearly have AG is a linear map between them. So it cannot be an isomorphism because these representations are given to be non-isomorphic. It must be the zero map by the previous Spur's lemma. AG is in zero linear map means AG's inner product of AG of applied at any vector with anything is 0. And this directly gives us that like the matrix corresponding any map to any two matrix coefficients are orthogonal. Even if they're isomorphic, in that case you'd have got AG to be lambda times an identity. And in this case, P and W can take to be orthogonal vectors to get that if they are not diagonal entries, this inner product will either be 0. That is how it proves that even for same representations, two distinct matrix coefficients are still orthogonal as functions. And the particular matrix coefficient has norm 1. This I had not proved because if in Schru's lemma, this P must be a scalar multiple of the identity map, but I haven't specified what scalar multiple is that. It most probably it would be like trace of T by dimension of T, something like that. I don't remember. And we can use that to show that these matrix coefficients are orthonormal. So here is the relations. We just try to remember that any two matrix coefficients coming from non-isomorphic representations are orthogonal. Even from their isomorphic, they are like basically they form an orthonormal type of setting. This is what we mean by screw orthogonality relations. We move on to the next thing. So we recall some of our things that we did before. For a representation rho, epsilon p, eta p was a span of f in v, so that there exists vw, so that fg is inner product of rho g v comma w rho. That is all matrix coefficients coming from the representation rho. This is same as basically the rho is a representation. It basically the rho representation, what does it do? It represents each group element by a matrix according to rho. And for matrix, it will have a lot of entries. That's entries, it will give you functions from G to some field, which will call which are some typical examples of matrix coefficients. All other matrix coefficients will be like scalar multiples, and they'll be generated by them, which we'll see later. We'll see that if rho and pi and isomorphic representations, then the matrix coefficients coming from rho and pi are exactly same. So for an equivalence class of representations, unitary representations, the matrix coefficients coming from an equivalence class of representation makes sense and it's well defined because for any two isomorphic representations, the matrix coefficients are same as spaces. Now we have seen that from the screw orthogonality relations that matrix coefficients coming from the sum of two representations, the sum of the individual component representations. If rho is reducible and pi is one of its simple components, then eta rho is clearly subset of eta pi, because let's say rho is direct sum of pi 1 and pi 2. Then any matrix coefficient will be written as sum of the matrix coefficients coming from pi 1 and pi 2. And that will be in pi always. So we can just focus on the simple components, because others will be the sum of them. This fact, so we can just focus on the simple matrix coefficients coming from the irreducible representation. That's basically important, because that's more important because the simple components, they form the basic building blocks of representation. So they are of utmost importance. So together, this fact with screw orthogonality relations, it implies that eta is direct sum of eta rho, because from non-simple representations, we can write the matrix coefficients as sum of matrix coefficients coming from simple representations. We can write it as sum of eta rho, where rho varies over all equivalence classes of simple representations. The direct sum is because of screw orthogonality relation. That is, if rho and rho prime are not equivalent, then the spaces eta rho and eta rho prime are orthogonal, because any two matrix coefficients from non-isomorphic representations are orthogonal. So there are spaces, that collections will be also orthogonal. And in most cases, like for a group G hat represents a dual space G, but here we are not meaning that. Here G hat is an enumeration of equivalence of finite dimensional simple unitary representations of G. We'll see that G hat is a dual group when G is abelian. This is a particular case. But if G is not abelian, it might not be. And again, it's orthogonality in eta rows. Eta rows is subspace of L to G. So its orthogonality is with respect to inner product in L to G that we defined at the beginning. So I'm moving to the next page. I think I'm almost running out of time. So for Hilbert spaces, their Hilbert space direct sum is defined as all tuples in the product space whose sum of squares of norm is positive. That is, this is the most obvious thing to do, because you cannot make the entire product to be a Hilbert space, because an uncountable sum of things might not make any sense. they might not converge, and like you cannot make a like norm structure there. So we only take things that are square summable. It can be shown. Oh yes, I think yeah, countably supported. I think yeah, countably, not finitely. I mean, actually, we cannot make sense of like arbitrary sum. Like we can only define sum for like. I mean, we can make sense, but suppose you have an uncountable index and we're summing something over an uncountable index. How do we define it? We can take any finite sum from that uncountable index and sum over it and take supremum over all of finite sums. This is how we define sum like an uncountable sum. We can prove that an uncountable sum converges if and only if the summands are non-zero only for countable many terms. So even if we define like sum for uncountable things, like it will not make sense unless our sum is countable. Now this is direct sum of Hilbert spaces. Now we can also like HIs are vector spaces and like particular modules. We can make their algebraic direct sum in the following by taking like finitely supported sequence that as you mentioned. It can shown that for if Hns are closed subspace of a particular Hilbert space H, then the algebraic direct sum Hn, that is finitely supported things, its closure is these are Hilbert space direct sum, that is all square summable things. They're isomorphic. I mean, they cannot be equal because one thing is subspace of thing, another thing is we're inducing another statement from the product. They're isomorphic. It can be proven. So with this, we have the like background to define like state the second Peter Weyl and prove it. So let's G be a second countable compact group. Second countable means it has a countable basis. That is, we have a countable collection of open sets so that given any open set and any point containing it, one of the countable collection member open set is inside that open set and it also contains the point, something like that. For any second countable compact group and our regular representation tau G2 unitary group of L2G, L2G become direct sum in the following way. It says that for every irreducible representation 0 of G, see this irreducible representation may not be a sub-representation of L2G. It can be from anything. Like G can, like topological group, G can act on any vector space and it can have any simple part. So there can be like too many simple parts of the group. It's so fascinating. It says that like given all simple representations of the group appears in L2G. L2G is so big. Like all simple parts appear in this. Like suppose it has 17 simple parts. In a representation, it is possible that only 3 of the simple parts occur. It's not necessary that all simple parts must occur in the decomposition of any semi-simple representation. But L2G says that L2 in the decomposition of L2G, all finite dimensional simple parts occur and it occurs exactly its dimension many times. This is our second Peter Weyl theorem. The statement is, and this direct sum is our like Hilbert space direct sum. We have an like wide head on the top of the direct sum. Let's try to prove this statement. One thing that we can do is as follows. We have seen that the matrix coefficients, they are dense in L2G. So instead of L2G, okay, let's try to first address why G hat is countable. Because this direct sum of Hn is isomorphic to like this direct sum identity. This is a countable direct sum. This might not be true for uncountable. So in these cases where things were varying over G hat, we'll try to use the previous result. For that, we need G hat to be countable. That is, we need a setup where we have only finitely many equivalence class of simple irreducible unitary representation of a compact group. This might not be true for any case, which we'll be talking in the next slide. So let's talk about it. The second countability of G is actually important. Otherwise, G hat might not be countable. For instance, we can take an uncountable collection of finite groups Gi, each equipped with discrete topology, so that they are compact topological groups. We can take H to be the product group. By Tichenov theorem, arbitrary product of compact groups is compact set is compact. So G is compact. It is not difficult to say that H has no countable basis because like by the definition of product topology, like only finitely many slots, like for any choice of finitely many slots, we need at least one member of the basis. So like basically you have an uncountable index and it will vary over all finite sets, and that will easily generate uncountably many elements of the basis. So in particular, it cannot have any countable basis. By universal property of product, giving a homomorphism from product group to another group is same as giving individual homomorphism from each group to that group. That is, if the target group is a like GL of V, that is a general linear group, it says that giving a representation of a product group is same as giving representations of each factor group. Arbitrary product always works here. Giving a representation of G cross H is same as giving representations of each G and H individually. And like we need choice of representation from one choice of representation of G and that choice of representation for each to get a representation for G cross H. This is our universal property. But what we can do is for each fixed index I, we can take a non-trivial representation of Gi and trivial representations for all other Gjs. They together combine to give pairwise non-isomorphic irreducible representations of H. And basically it says that H hat has cardinality at least as that of the indexing set, and we have taken indexing set to be uncountable. So this is not right in our case. So G hat might not be countable in general. So we need some additional hypothesis. We claim that G being second countable is enough. This follows from the next level. It says that if X sigma mu is a separable measure space, that is, the sigma algebra can be generated by a countable subset of them, of the big sigma algebra. For a separable measure space, LP becomes a separable metric space. So using this lemma, we can directly say that if G is second countable, then L to G is separable. Now, an orthonormal basis of any separable Hilbert space must be countable. Why? Because for an orthonormal basis in an Hilbert space, any two members of the orthogonal family must be like square root 2 distance apart, like norm of EI minus each over square is 2. So basically, if it is separable, it means it has a countable dense subset. So what we can do is, since any two basis elements are square root 2 distance apart, we can take any distance d less than square 2. Let's say 1 point very small thing. Let's say d is our distance. So we can, around each basis vector, we can take d radius balls, and this all d radius balls will be usually they will be disjoint. And what we can do is basically if it is separable, it has a countable dense subset. So that dense subset has to be dense in each every ball. So we have uncountably many disjoint balls, and we have members of the countable set in uncountably many disjoint balls. It will clearly mean that our dense set is also uncountable. So a separable Hilbert space that has countable basis, like countable dense subset, its basis must be countable. I mean the orthonormal basis. So since L to G is separable, all its subspaces must have countable basis. So since in particular eta, like the space of matrix coefficients, they're clearly square integrable. It is a subspace of L to G, so it has a countable basis. Now eta is direct sum of eta rows. That's how we defined eta. And each eta row is spanned by finitely many matrix coefficients coming from the finite dimension representation of V row. Why? Because we call eta row. Row was varying over like finite dimensional equivalence classes of irreducible representations. If V row was the irreducible representation, basically what we do, each group element G is represented by let's say V row has dimension D row. Then each group element G is represented by a D row cross D row matrix. So this gives us like basically G goes to rho ij of X, and ij both vary from 1 to 0. This basically gives us d rho square. The matrix has d rho square entries, and as two orthogonal relations, all these are orthogonal functions. This gives us d rho square many orthogonal matrix coefficients, and they span the entire of eta row. So each eta row is finite dimensional. So if G hat was uncountable, it would mean that we have uncountably many eta rows. Now since each eta row has finite basis and we have uncountably many of eta rows, it will clearly give an uncountable basis of eta. But we have already seen proven that eta cannot have any uncountable basis. So this indexing set G hat, it must be countable. So under the assumption of second countability, we can claim that we can have at most countably many irreducible representations of G up to unitary equivalence. So after this, let's try to prove the main theorem. I guess I am out of time. I have only 4-5 slides left. I need 10 minutes more. So for a proof, note that it is enough to show that instead of L2G is isomorphic to the Hilbert space direct sum of 0 to the power dim 0, it is enough to show that eta is isomorphic to 0 to the power dim 0. Because eta is, by the first Peter Weyl, we have shown that eta is dense in L2G. You can take the closure on both sides. Eta closure will be L2G, and this closure over this direct sum will give us Hilbert direct sum. So it's enough to prove this first centered equation. I mean, not equation, isomorphism, whatever. Note this, eta P has already an unitary representation structure of G by the following action. So eta rows elements are matrix coefficients. A group element H acts on a matrix coefficient in the following way. So rho G was a representation we twist it by H inverse inside our rho. This is the only thing that we can do. We cannot apply H at anywhere else otherwise. So first we show that eta rho is finite dimensional. This I have already shown. It has dimension 0 square. There are matrix entries rho I j g. This functions I j from 0 carrying to 0. That is the matrix entries of 0 cross 0 matrix. Like they form the orthonormal basis of the matrix coefficients coming from 0. So dimension eta rho is in particular 0 square. We have seen that finite dimensional representations of compact groups are semi-simple. That is, eta rho is direct sum of simple representations. Now, by our definition, by our nomenclature, all simple finite dimensional representations are indexed by some v eta for some eta in G hat. Now, by screw orthogonality relations, if alpha and eta are not equivalent, then eta alpha and eta are they are orthogonal. Like what I'm trying to say is that eta rho decomposes as direct sum of some vi's, some v rows, not rho. Eta rho decomposes some v pi's, where pi varies over some g hat. Now, apart from v rho, no other v pi can be present in the decomposition of eta rho, because v pi is orthogonal to 0. This is what I'm trying to do. Like screw orthogonality relations, like a subspace of a space cannot be orthogonal to the whole space unless it is 0, because inner products are non-degenerate bilinear space. So basically it means that apart from 0, no other non-isomorphic v alpha can appear in the decomposition of eta. So in the representation decomposition of eta rho, only 0 can be present. So eta rho must be some power of 0, like only some copies of 0. Now n has to be dimension of 0. This we can directly compute by just taking dimension on both sides, and this proves our Peter Weyl theorem. And after this we have a nice corollary. It says that all irreducible representations of a compact group G are finite dimension. This might not be true for locally compact groups. We have infinite dimension irreducible representations of R. For a proof, let's say our strategy will be to like this. So see, irreducible representation might not be inside L2G. We'll try to show that. So that idea is L2G is so big that given any irreducible representation, we should have a copy inside L2G. So given any infinite dimensional irreducible representation of G, we'll try to make a copy of it inside L2G. And we have already decomposed how L2G looks, and we'll use that to show that infinite dimensional irreducible thing cannot happen. This is our idea. So basically, it's v pi to be an infinite dimensional irreducible representation of G. We can embed v inside L2G in the following way. fix and W in V and consider the linear map T from V to L to G by TV of G is inner product of pi GV comma W. Sort of like basically you're taking a vector W, fixing it, we're trying to map V inside L to G by generating a lot of matrix coefficients. We're identifying each vector as a like matrix coefficient inside L to G. You can check that T is a G linear morphism. We show that T is injective, otherwise the embedding word will not make any sense. So by adjoint test, T is same as inner product of V of pi of G inverse of W, because like pi is an unitary representation. So if T is 0, let's say, then V is orthogonal to pi GW for all G. So V is orthogonal to span of the pi GWs when G varies over G. Now note that the set pi GW where G is in G is itself invariant, because like we apply pi h. Pi h of pi G of W is pi of G h of W. It is again of the form pi of G of W, where G is replaced by GH. Like the vectors G dot V, where G varies over G, it's a stable, is a G invariant set. Its span is also G invariant subspace of V. Since V is irreducible, all G invariant subspace of V must be either 0 or the full thing. It cannot be 0, obviously, so it is the full thing. So the span of pi GW, where G varies over all group elements, is the entirety of V. Since our initial vector V was, so we are taking a V to be kernel of T. We have shown that V is perpendicular to span of pi GWs. Since we have shown that span of pi GWs is same as V, it shows that V is orthogonal to the entirety of V. This cannot happen for non-zero vectors. So V is 0, so T is injective, and we have found an isomorphic copy of V inside L to G. This is what we mean by L to G is so big, because all irreducible representations, even finite or infinite, doesn't matter. We can find a copy of all irreducible representations inside L to G. Now we find a contradiction by showing that L to G has no infinite dimensional simple subrepresentation. If it exists, it cannot be isomorphic to any finite dimensional simple subrepresentation of L to G. Basically, because an infinite dimensional space cannot be isomorphic to a finite dimensional space, of course. So it must be orthogonal to each zero by Spruce lemma, because they are not isomorphic. So it must be orthogonal to the direct sum of all zeros. However, our previous Peter Weyl theorem says that all finite dimensional zeros make up all of L to G. So if an irreducible infinite dimensional subrepresentation of L to G exists, it has to be orthogonal to all finite dimensional components. Now the finite dimensional simple components make all of L to G. If it is orthogonal to each component, it is orthogonal to the direct sum of all the components. Since the direct sum of all the components is basically L to G, it means that if an infinite dimensional irreducible subrepresentation of L to G exists, it must be orthogonal to all of L to G, which is again not possible. A subspace, non-zero subspace of vector space cannot be like orthogonal to the big thing. And we are done. So it says that again all irreducible representation of a compact group are finite dimensional. We will finish this talk by giving a short example. We first note that if G is an abelian group, then all irreducible representations of G are one-dimensional. Abelian, it can be abelian topological group or an abelian finite group, whatever. This is true because if V is an irreducible representation of G, then all rho G's are G invariant linear operators. By screw lemmas, because of abelianity, rho G, rho H is same as rho H, rho G. We are using abelianity, the abelian nature, to show that all rho G's are G invariant linear operators. By Spruce lemma, all rho G's are scalar multiples of the identity. So let's say it is lambda G times identity. Now for any fixed B, by a similar argument, we have V is same as span of pi G of V. Now pi G of V is same as lambda G, because pi G acts as lambda G times identity operator. So span of lambda GV of V, and it is span of some scalar multiple of V against subset of span of like the whole span of V. It directly means that the irreducible representation vector space B is same as span of V. Again, it won't be capital V, it will be small v. I mean, if V is spanned by a single vector, small v, so it is one dimensional in particular. So any irreducible representation of an abelian group is one dimensional. This is what we have proven. We'll try to use to prove something in Fourier analysis. We'll work with our G to be the circle group S1 with Lebesgue measure. by the discussion above, all irreducible representation of S1 are one-dimensional. That is continuous homomorphism from S1 to C cross. Now, since each rho z is an unitary operator because of unitary representations, so rho z star is same as rho z bar, which is norm rho z square is 1 because you are in S1. So directly means that all continuous homomorphisms are continuous maps from S1 to S1. It is a standard topological fact that all continuous homomorphisms from S1 to S1 are of the form z goes to z power n for some integer n. How you can show that? We can show that S1 is isomorphic to, like, homeomorphic to R mod Z, and so our idea would be to, like, first classify all continuous maps from R to R, which are linear maps, then classify all R, like, linear maps from R to S1, and we can use that S1 is the covering space of R and so on. It's not very obvious, but it is standard. I mean, it is very well known.
Maybe we can directly use the fact that it's a homomorphism. We'll get something related to Cauchy functional equation, and since it's continuous, we'll get that as a solution.
Actually, Cauchy functional equation, we need to, like, from multiplicative to, like, additive, we need to take log.
Yeah, you have to take a log. That's why you get nz instead of z to the power n, right?
Yes.
So if
But
chi
log
is the
might be-
character, then
Yes.
log chi will satisfy the Cauchy functional equation, and by continuity, we'll get that directly. Covering space might be more direct, but this also.
I think we're on C cross now. So, like, to define log, we need again to take branch cuts or something.
Yeah.
I mean, we're not
But-
real. In real, it would be easy, R plus.
Real it would definitely be easier. Okay, anyway, you continue.
Okay. So it is straight. Okay. So it's from Z goes to Z power n. You can, like, represent it map as e power ix goes to e power ix by rho n. Then clearly it's a one-dimensional space, so the matrix coefficient will also be formed by this single function because it's a 1 cross 1 matrix with one entry. That single entry will give me the matrix coefficient. So, like, the matrix coefficient of this one-dimensional representation rho n is same as C span, like the C span of e power ins, this function. Using this, we try to prove the following result. By the Peter Weyl theorem, we have L2 of S1 is isomorphic to the Hilbert space direct sum of C e power ins, like the C span of e power ins. Since topologically S1 and R mod 2 pi z are same, we have found that L2 of the interval 0 to pi is isomorphic to the Hilbert space direct sum of C span of e power ins. Now this isomorphism gives us a useful thing. That it says that f is on LHS is same as f is on RHS. So it means that, and this isomorphism goes as follows, like, given any function on the RHS on the n component, it will give to the Fourier coefficient f hat n. It says that for a function, it is 2 pi square integrable. It's like basically a 2 pi periodic function is square integrable if and only if its Fourier series converges in L2 norm. Again, these are like classical Fourier analysis stuff, but this is a nice application of the theorem. That's it. And this ends our talk. Here are the references. So our main references is Haar, and Peter Weyl theorem, like 2 sections from Terence Tau's notes. Terence Tau's blogs rather. And I have found, like, a few handful of topics from, like, Stein's book, Topics in Harmonic Analysis.
So one question in the previous slide, the isomorphism that we had, that's in fact also a isometry, right?
Yes.
For L2, it happens to be an isometry, but can we say that it's for general spaces? For example, in S1, yeah, but in general also, I think for as long as you're dealing with locally compact groups.
I think Peter Weyl is true for compact groups, I think.
Okay, let's take compact only. But yeah, I don't know. I mean, maybe that is Parseval's theorem or something. I'm just asking. I don't know this properly.
Parseval's theorem, I don't recall properly. It's something about integration of, like, the Fourier transform something.
Yeah, the L2 norm of F and the L2 norm of F hat. They happen to be
if
the
had
same.
yeah, they're same.
Yeah. So I think that is sort of
Happening here because it's
going on here.
it's an isometric isomorphism or something like that.
Yeah, maybe I'm just saying.
Yeah,
Or
I'm also
there
not
might be
sure.
some further complications involved also.
Okay.
Because the result I had read that was for locally compact. So that was a bit more general, and so it wasn't an exact isomorphism. You have to restrict to further smaller subspaces somewhat.
I see.
So anyway, let it be.
Okay. I think does anyone else have any question?
Okay, then if nobody has any further questions, let's thank Ritabrata for this wonderful talk. So okay then, thank you so much, Ritabrata. We did go a little bit over time, but that's not much of a problem.
And it's a lot of material.
Yeah. It was a lot of material. Okay then. Bye guys.
Thank you. Yeah. I will end.